Okay, so sorry, I should have kept the video going on that last one. In a previous video, we determined the chi-square test statistic for this information is 18.549. So the next part is we're supposed to find the area to the right of the chi-squared value. So tables of values like this one up above and the back of books are chi-squared values that correspond to like a right-tailed area. Okay, it's with the normal distribution. Oftentimes, whoops, I don't know what happened there. With the normal distribution, oftentimes we want to know like the area that's to the left of a certain value or the area that's to the right. But for chi-square tests, I can't think of any off the top of my head that are left-tailed. They're right-tailed tests. Okay, so the tables in the back of books tell you the area to the right. So we looked up this alpha of 0.10. So that's our area to the right of that chi-square test statistic. Okay. Let me see if there's anything else. That's it. Okay. Okay, for this question, we're supposed to pick from these three chi-square tests. Before we do that, just a quick idea of what each of these mean. The test of independence is when you're trying to compare two categorical variables and you want to see whether they are, dependent on one another, whether they affect one another, or whether they're independent of one another. Okay, and this is usually where you see a contingency table. So if you can imagine the data being put in like a table like this, where maybe this is gender, and then this would be, let's say good, okay, or bad, some sort of like categorical rating or some sort of category you can put them in. You could test to see whether gender is independent of ratings or whether gender, if it's true that gender is dependent on ratings, that means a person's gender is impacting what their ratings are. Okay, so that's a test of independence. A goodness of fit test is a test to see whether your data follows a certain distribution. So we do this like if we want to check to see if our data is normally distributed. I guess a lot of questions we're going to see in Newton are going to be questions where there's an expected amount, and then there's what we actually get with our data. So actually they usually say observed here. Observed. Okay, so again, you could put these in columns. That might make it confusing with the test of independence, but just remember, the difference is the goodness of fit test is comparing some expected amount to some observed amount. So maybe, like based on some previous theory, you expect to have 20 of some variable one day, 40 of them another day, and then I'm just keeping it simple here. We actually get 30 one day, 30 another day, and 20 on the third day. You could test and see whether your observed numbers, the data you actually collected, you could test to see whether it's different enough than this expected amount. Okay, and those numbers are certainly different right now, but they might be close enough to the expected amount so that we can't say it with certainty. That's why we use statistics. Okay. So that's a goodness of fit test when you compare your observed amounts to your expected amounts. And the test for homogeneity is a test to see whether two columns of numbers come from the same population. So like you've got blood pressure for one group of people, for group A, and you've got blood pressure from group B. You can test to see whether these two came from the same population or not. Okay, so now we know the three of those. Let's check out the problem here. A hospital is trying to compare the weights of babies born at night and babies born during the day. They collect a random sample of weights for babies born at night and during the day and record the distribution of each. They want to compare the distributions to see if they are the same. So which of the following chi-squared tests should be used in this situation? So that matches a test for homogeneity like we were talking about. We're trying to see if those two babies have the same, are coming from the same population. If this test is significant, then we're going to claim that babies born at night have different weights than babies born during the day. Okay. Okay, the chi-square goodness of fit test is a test to see whether your data comes from like an expected distribution. Like let's say, just a real quick example, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. One person says the number of customers we get every day is the same. Okay. expect 1/7 of our customers to come on Monday, 1/7 to come on Tuesday, 1/7 to come on Wednesday, etc. Okay, but we can compare that to our actual data and use a chi-square goodness of fit test to see whether they really did all come from one day. Like maybe we got 2/9 here, 1/8 here, etc., etc. There's some differences, but maybe the differences are just because of random error. Maybe they're not. Maybe the difference between the data and the expected are because of just random chance. A chi-square test can tell us whether it doesn't seem to be from random chance, whether it's too extraordinary. Okay, so that's the basis of a chi-square goodness of fit test. So a survey company puts out a survey asking people 2 questions. First, it asks if a person uses public transportation. Second, it asks whether or not the person supports an upcoming environmental protection bill. The data are recorded in a contingency table. The company wants to determine if support for the bill is independent. So this actually sounds like a different chi-square test here. Okay, so they're making some sort of contingency table. Maybe I didn't pay too close attention to what the variables are, but there's 2 variables. There's a category up here, and there's a category down here. Okay, so this is called a chi-squared test for independence. Okay, you're testing to see whether these 2 categorical, in other words, these 2 qualitative variables are independent or dependent on one another. That's different than a chi-square goodness of fit test. Okay, so if you're working on a different question, if they're trying to compare 2 categories and see if they're independent, that's a chi-square test for independence. Okay. So let's check out the next option. A researcher is trying to determine if boys and girls spend a similar amount of time on homework. He surveys a random sample of boys and girls in schools and records the distribution time spent on homework of each gender. He wants to determine the distributions are the same. So really, if you got 2 columns of numbers and you're trying to determine if they come from the same population or not, that's a chi-square test for, I don't know how to spell this word, homogeneity. Okay, that's when you test to see if 2 variables come from the same population. And with all these tests, there's different versions of the test where you can expand it. It doesn't necessarily have to be just 2 variables, but that's just what you commonly see. You got one set of data, you want to see if it's the same as a different set of data. So we got the column of boys, column of girls. We want to see if they come from the same population. That's a chi-square test for homogeneity. Okay, so that's not it. We're supposed to find a chi-square goodness of fit test. A referee wants to make sure the coin he uses for the opening coin toss is fair. He flips the coin 30 times and compares the number of heads and the number of tails. So that sounds like our first example, which is a chi-square goodness of fit test that we said. Okay, instead of Monday, Tuesday, Wednesday, Thursday, Friday, we've got heads and tails. I'm just going to use T for tails. Okay. So the heads column, we have an expected amount, 1/2, and we expect 1/2 to be tails. But then we can actually fill in the data. It might be like 3/8, and this is 5/8. Okay, and then we can run a chi-square test for goodness of fit to see whether it's really a fair-sided coin or whether it's biased in some way. Okay, so anytime you do that, where you compare some actual values to to expected values, you're probably talking about chi-square test for goodness of fit.